Hey everybody, welcome back. So this is lecture number 22. We're going to talk about ensemble methods and kind of finish up with what we started with random forests. This time around, we're talking about boosting methods. So random forests are a bagging method, and this time we're going to talk boosting. We'll chat about AdaBoost and gradient boosting just a little bit. Well, let's get into it. But before we do, I just want to kind of give you an idea why we're talking about ensemble methods at all. I would say that, there are maybe three big thrusts to recent machine learning research, right? There are the neural networks, which everybody knows and loves is the main buzzword at the moment. And we've covered support vector machines. The third one are these ensembles. And at various times, all three of these have traded back and forth the crown of what is the coolest, hottest thing going, okay? And it's not that any of them ever get replaced. That's not quite right. What happens is that through the course of research, when something becomes very new, it attracts a lot of interest, and some new breakthrough gets everybody going towards it. The other stuff doesn't go away, it just kind of slows down in development because everybody's attention is elsewhere. So it's been interesting to watch how these things have teetered back and forth on the bleeding edge on what's cool. The neural networks were the big deal when we revived after the AI winter, right? And then support vector machines had all these wonderful guarantees and this clear theoretical basis and had a lot of good results. And then it was kind of ensemble's turn, right? And random forests and boosting took off. Actually, you would really say the boosting started in the late 90s, but really took flight after random forests did, when various modifications were made. And then SVMs made a comeback because brand new computational techniques allowed you to do SVM, or at least linear SVM, not kernel, allowed you to do linear SVM with very large kind of internet-sized data sets, which, as many of you are doing the project right now, may be experiencing. SVMs with large data sets can be quite slow, especially when C is not in your favor. Okay, and then after that, we got the deep learning revolution hitting and kind of a revamp of boosting coming back in the late 2010s with techniques like XGBoost and LightGBM. Okay, so that history hopefully gives you an idea of why we're talking about this stuff. So what is boosting? What exactly is happening here? How is it different than bagging? Because we've talked about bagging already. Bagging is a process where we resample, I shouldn't say iteratively, where we just resample the data and train a classifier with this resampled setup. Okay, so each classifier in the ensemble gets a different random subsample of the data set drawn with replacement. That's bagging. And also, if we're doing a random forest, then not just that, but then every node in the tree is going to be constructed from a random subsample of features as well. Okay, so bagging is inherently parallel because each classifier is just its own resample. Okay, so there's no reason to do them in a line or sequentially. Boosting, in contrast, is an iterative process. It is going to be sequential. We make the first classifier and we train it, and then whichever data points it makes bad mistakes on, we flag up those mistakes and we say, hey, next classifier in the line, you really need to pay attention to and fix these mistakes that the last classifier made. So Each classifier in the chain can be a weak learner, and in particular with AdaBoost, we can basically guarantee that almost, as long as it's just a smidgen better than chance, that we can get a strong learner out of the boosted ensemble, no matter how weak the individuals are in the ensemble are. So, and as I've already mentioned, there's two types of boosting, which differ in how weights are updated and classifiers combined. And adaptive is AdaBoost, and gradient is XGBoost. All right, so let's just kind of throw out these citations for you. So if you want to see what's what, here's some papers that will give you a strong understanding. So again, adaptive boosting and gradient boosting come from the same boosting framework, but their implementations are different. So what does a boosting classifier look like? We start with our training sample, and we weight it, okay? Every single sample in that training set is got a weight attached to it. So when we learn our algorithm, we try to minimize not just, say, misclassification error, right? So here's this one, that's the math RM1 is our misclassification error. It goes to 1 if h of x is equal to, sorry, this is not 0, this is not misclassification error, my bad. It is the 0-1 loss, right? And when h of x is equal to the target I, then this value becomes 1. And if the output of our classifier h is not equal to the target, then this value is 0. Okay? So this 0-1 loss, I almost said it again, is the standard thing that we know about, right? When we get 1, we like it. We have properly classified an input. Okay? And you'll notice here this weight, each one of the samples is got a weight attached to it. So what we're trying to do is, instead of just maximizing the 0-1, maximizing the accuracy, right? What we're going to do is we're going to try to maximize the accuracy with each element multiplied by its own weight. Well, how is that weighting thing working? What is that doing? Well, every time we start with a training sample, and again, we have the sequential setup where we go through the first classifier, and that feeds to the second and the third and the mth in this case, right? And each one of those classifiers is outputting a prediction, and each one of those classifiers is producing, some errors, and every time this classifier makes an error, the next classifier in the line is going to get a weight for that sample that's high. We're going to make that sample worth more and make the classifier that's next in the line try harder to make sure that problem is solved. All right, so this line here that I've been working on is the AdaBoost line. It has the 0-1 loss in it. The gradient boost has no such loss in it, right? It doesn't have the 0-1 loss. Why is that? Well, you might guess that a gradient boost works by gradient descent, and you'd be correct there. And there is a problem with the 0-1 loss, right? It's discontinuous. So if you have a discontinuous function, you can't really do a gradient. So we get rid of that for the gradient boost machine. All right. So here's that general boosting idea written as pseudocode-ish, right? So we're going to initialize, we have two weights in boosting, okay? We have the sample weight, which we've kind of already been discussing, okay? The sample weight is this W, where what we do is we we want to try to, for every time we make a mistake in the last one in the chain, we're going to try to correct that mistake on the next one in the chain. So I'm showing that in green. That's the sample weighting. We begin everything with the sample weights equal. Every data point is worth the same for properly classifying it. Okay? Then we loop, and inside the loop, we create more and more classifiers in a sequential manner. Okay? Each time what we're creating is a weak learner that tries to minimize the misclassification error or maximize the 0-1 on the weighted data set. Right? So again, those weights say whichever mistakes were resulting the last time, we're going to try harder to undo those. Okay? After we produce a classifier that does this, it's minimizing the weighted misclassification error, then what we're going to do is we're going to calculate a classifier weighting. So each one of these classifiers in the ensemble has to be recombined. And that is what I'm calling the classifier weighting right there in yellow. So once we take all the methods in the ensemble, put them together to create an output, we need to weight each method inside the ensemble. And what we're going to do is we're going to say, hey, classifiers that have made fewer mistakes, they get to vote more. And classifiers that have made more mistakes, we care less about you. So one key is that at every time step, like I said, if we make a mistake with something, we're going to go ahead and pull it to be more important. We're going to make sure that the next classifier cares more about it. Also, if we do something right, if we classify a sample right, then we're going to flip-flop, we're going to reduce its weighting. All right? So the key element here is that the green, the sample weighting, gets calculated as a function of the yellow, of the classifier weighting, right? So each time if we make more mistakes overall, then the sample weighting is going to be different than if we make fewer mistakes overall. All right, in the end, we go ahead and we predict the output of the whole ensemble, like I said, based on a weighted majority vote. So let's show it in action. So we have our usual setup. There's a training set, okay? Only this time our training set doesn't just have X's and Y's, it has a distribution D. So I'm flipping notation here because I have two different sets of slides I've borrowed. Okay, so just for your edification, D is W from those previous slides. All right? It gets worse, by the way. These different papers running around, they all have different notation for these. So the notation for doing boosting in the Hasty and Tibshirani book, totally different again. All right, so anyway, back on track. What are we doing? We have our inputs, we have our labels, and we have a weighting for every single sample in the data set. All right, our inputs are reals, our outputs are binary classes. So here's what our positives are red, negatives black. And what we're going to do is we're going to try to minimize the total training set error. So this is the training set error E. And what is the training set error? Again, it's the sum over all of the elements in the data set, weighted, and this is the 0-1 loss. So when this is, so now it's actually a loss in this case, right? So when we're saying when the output of the classifier is not equal to the true label, then we get a loss, we get a 1. Okay? So this is now the error rather than the accuracy. Previously, I should have reported that as the accuracy because it was not a not equals, but an equals. All right? Sorry for the confusion. But now it is truly a loss because it's a not equals. We have, every time we make a mistake, we put a 1 in here, and we sum up all the ones multiplied by their weights. Okay, so we've got some data points. Let's try to separate them. So in the beginning, we have a set of weights D. And again, we're going to start those weights as being all equal, which is shown here by the size of those dots. When a dot gets a higher weight, it's going to get bigger in this little scheme here. Okay, so we're going to train a decision stump, right? The dumbest thing we can possibly put into a classifier. Do you remember what a decision stump is? Yes, you, Charlton Heston, front row. No, I can't talk with you about the NRA right now, Charlton Heston. Okay, I'm going to call on Jeff Bridges, middle row. No, Jeff, we cannot. No, we're not drinking White Russians now. Okay, I need somebody who's ready to talk to me. All right. Ashley Judd. Okay, great. Finally somebody who's willing to talk turkey here. All right, so Ashley's right. What a decision stump is all it is it's the root of a decision tree. It is merely a thing where we're going to look through all of the possible variables and we're going to scan through the variables looking for a place to put our separator line, which is going to best minimize this training error, right? So it looks like this. We're going to scan through x1 and x2, right? So scan across looking for the best place to separate black and red dots. Well, it turns out that that place is right there. Okay, and everything on this side is going to be labeled as a negative, and everything on this side is going to be labeled as positive. All right, so that's our threshold, and we make our decision boundary, right? It's just the sign. Whenever x1 is less than the threshold, it's a positive case. Okay, so what is the error here? Here are 3 misclassifieds. So our error is 3/9. And I haven't really run you through it yet, but we're going to do the misclassification error here through this formula. So this is, sorry, not misclassification error. This is the classifier weighting, okay? Alpha is the classifier. Actually, I should undo that. Alpha, we'll do it in the yellow, is the classifier weight. So this is going to tell us when we come back what, how much each one of the classifiers in the ensemble gets to contribute to the overall decision. Okay, so there we go. We're going to calculate it. As I mentioned to you in the past, this classifier weight is a function of the overall misclassification error. So if you get better, your classifier weight does too. So we've made 3 out of 9 mistakes. This is our classifier weight. And we're going to reweight everything in the data set for the next go. And we're going to reweight it according to e to the minus alpha. So we're going to take the classifier's weight and run it through an exponential and use that exponential to either bump up in the case of a misclassification or bump down the weight of each data sample. All right, so that results in D2, which is a modification, a multiplicative modification of the original weighting. Okay, So what does that look like now? Well, those 3 ones that we made a mistake on, whoops, they are much higher weight now, and everything else is smaller weight. So we're going to rerun the classification, the same kind of decision tree, right? So we're going to scan, try to find the best possible separator. We're going to check both directions that are available to us. Okay, and it turns out that this is where we're going to throw our dividing line down now, right? So what happens here? Well, at this point, the positive case is still negative, so it's like less than this threshold. So these are the errors now. Okay. But these errors are worth less than the ones back a minute ago, right? So these data points are a higher weight than these data points. So even though it's 3 out of 9 are wrong, it's these 3 multiplied by their weight, right? So it's now less than 3/9. That is the actual epsilon, the training set error. Okay, so we do it again. The training set error tells us what the classifier's weight is going to be. And then the classifier's weight, again, is used to bump up our 3 mistakes, our black mistakes, and bump down everything else. So one more time, we now have D3. And in D3, we have our misclassified points are very highly weighted, and everything else is much less so. We'll do this whole thing for the very, very, very last time, I promise. Scan our decision stump back and forth, finding the place where the threshold is best. And it turns out that it's there. And this time, our threshold is such that when x2 is bigger than the threshold, then that's the positive case. So our misclassifieds are these 2. And again, because their weight is low, because they were previously bumped down and not an error on the last time around, their error is lower again. We get our classifier weighting this time is 0.92. All right. So the final classifier, the output of the whole ensemble, is just the outputs of each one individually, right? This is H1, H2, and H3. And each one of them is weighted by alpha 3, alpha 2, and alpha 1. Okay, so just take a moment. We got into the nitty-gritty. All that's happening here is that each classifier is trained to fix the mistakes of the last one in the chain. The mechanical details can get kind of overwhelming. So we're doing a weak classifier, right? And if you take those 3 decision surfaces that we just saw and add them together with their weights, right? Here's threshold 1, there's threshold 2, and threshold 3, and we join them together, we get a complex decision surface which perfectly classifies the training set. There are no mistakes here. So here's our output. There's these ones here are the alpha 1, alpha 2, and alpha 3. Oh, you can start to see how this works. I love it when a plan comes together. So, and again, the output H is really just, a simple decision threshold because this is a stump. All right, so here we get the pseudocode. So this is just a recap of everything we said, right? We take our training data. We have, in the beginning, a weighting which is even. Every single one of those are, whoops, I should not use yellow for that. I have a code, right? So green, that's our weighting of the sample. Yellow, that's our classifier weighting. And that exists down here too. And there. So when we update, as I said, we bump up everything which is, misclassified, and we bump down everything that's not. Right? One thing which is a little different here is you see that there's this Z, which is a normalization factor, and we choose that so that the weights are a distribution of probabilities, right? So it actually works so it sums to 1, right? So we want the sum of all the D's to be equal to 1. So that's kind of critical. All right, you'll also recognize that this thing here, well, we can get rid of that kind of if statement stuff. And we can do that by putting in the y right there, right? So when the y is a positive class, then everything's positive, and it rolls through as if the positive if statement, and when it's negative, the negative sign flips. Okay, great. So that is the AdaBoost algorithm. Oh, and I had the animation built in. So again, you can see where things are, right? The 2 different weights that we use in this algorithm. All right, at this point, it's been about halfway. I want to take a short break, and when I come back, we will talk a little bit about the properties of AdaBoost. See you in a minute.